email that, and then I'll upload the link. Upload the link when we're done. Okay. All right, so let's go ahead and get started. Whoa. All right. So what we're talking about is physical development between infancy to about the toddler years. And we're starting with birth. I'll probably have a reading assignment that gets into conception to birth, so that we cover that information as well. But I want to start with infancy, okay? So the first thing I want to do is talk about some brain development issues and some misnomers about it. And then we'll go over kind of the nervous system. So when we get to certain points, you kind of understand what we're talking about. And then we will get into the different physical trajectories within infants. How do they grow? What grows first, second, third, all those kinds of things. So the first thing that I do want to just state is, unlike the what we've been told probably since childhood, we use more than 10% of our brain. The old notion that we only use a portion of our brain is gone. That assumption came from the day in which we understood that we probably our learning and memory capacity, we only reach about 10%, but we use our entire brain, and it's completely active and it's completely running all the time. In fact, it's one of the few organs, except with the heart and breathing, that actually doesn't take a break from the time we're conceived to the time we are passed away, as you would say. The other thing that I need to mention is the brain and the body are not separate. As the brain develops, as we will see, we see physical growth within the body. So as I mentioned, since the beginning of the class, we're actually born, humans are born with an underdeveloped brain. And as our brain matures, our physical body also grows and develops into what it becomes by the time we hit full physical development through puberty. There's a direct association between the growth of the brain and our physical maturation. And as the body tries new things, the brain develops. So we'll talk about rich environments, stimulating environments are important for children, lots of activity, because as they're engaging in those activities, especially infancy through the age of 6, their brain is also developing and creating new connections and the like. So we need to make those claims kind of up front, okay? So just kind of explain some of the developmental processes that goes on. That go on starting with infancy. We're born with approximately 100 billion nerve cells in the brain when we're born, but the synapses between those neurons don't start to develop until after birth, okay? And so the synapse is what creates nerve cells to communicate with each other, okay? And so if we look at this cell here, you'll note that our nerve cells don't actually touch each other. There's a little what's called a synaptic cliff, in which neurotransmitter from one cell is released into the synaptic cleft. And then once enough of those neurotransmitters are received by the postsynaptic dendrite, the receiving cell, that's when we get a chemical electrical reaction down the cell. And that's That's one of the things about our nervous system is it is an electric system. It starts with a chemical reaction and then creates an electrical wave down the cell using, again, chemicals of sodium being released and taken in by the nerve cell. Okay. There is, especially within the neural area of the brain and down in the peripheral nerves of the brain, there's something called myelination. And this is something that we'll talk about in overall development. Is myelin, there are these little fatty nodes that go over the cell, and you'll see there's a little gap in between them, and they're just little fatty. One, they provide protection, insulation for the nerve. Okay. But the other thing it does is it increases the transmission of the electrical signal. So as the more myelin we have in our brain, the faster the brain we have. Okay. And we can always illustrate what's meant by how does it speed up the nerve cell, is if we can imagine this crazy little line represents an unmyelinated nerve cell. This one, I'm going to say, and I'm going to put little myelin sheaths on it. So we'll go here, here. Sorry about my artwork. And here. So without myelination, the electrical signal goes all the way down here. And I just want to illustrate the amount of time. So it do. And here it is, the electrical pulse is going down the cell. And as you can tell, it's kind of a little slower movement. But when we have myelination over the cell, the electricity jumps. So I want you between each of the myelin nodes. So let's see how quick this is. Boom, boom, boom. And so as you can see, if you want to think about it, it's like speeding up the cell by a multiplication of about 1,000. Okay. When we're born, we do have myelinated cells, but we largely have an unmyelinated brain from infancy to puberty. Okay. And then during puberty, our brain almost becomes completely myelinated as we go through the puberty stages. It's about a 6-month process. Okay. And we believe this has an evolutionary purpose. Okay. When you have a slower unmyelinated brain, you have a brain that is designed to learn and remember, because with that slowness, those connections are going to be made much easier and a lot better. So when you have like a 3-4-year-old that asks you the same question over and over and over, it's because their brain is learning with a slower mobile unit. But once that is learned, it sticks a lot better than when our brains become myelinated. Okay. Now, why do we then, when we become physical adults through puberty, does our brain speed up? Well, it's kind of a protection thing. So we have a slower brain through childhood, which helps us learn better. But I want you to imagine a child versus an adult. There's a car speeding at you going 50 miles per hour. As an adult, you're going to jump right out of the way of that vehicle because your brain has that fast reaction to it. But the child with the slower brain will probably sit there, and unless there's someone to save the child, they might even get hurt because their brain is processing that information much slower. Okay. And when we get to adolescence, we'll see that what you call the quote unquote craziness of adolescence has less to do with hormones and probably has much more to do with the fact that in 6 months they went from a brain that was going 20 miles per hour, and now they have a brain going 2,000 miles per hour. And there's a lot of mounting evidence that adolescence has less to do with our hormones and has more to do with this much faster brain that we have. And I'll bring this example up again when we get to adolescence. So when you ask an adolescent why they did that and they say they don't know, they probably really don't know, because their brain did something that they haven't processed yet. And we'll even talk about parenting when we get to adolescence. We find that adolescents who have an easier adolescence without all the turmoil versus those who have the turmoil have two different types of parents. The parents with children who tended to have rough adolescence, when they did something wrong, they asked them what they did, and they said, I don't know, and says, well, until you figure it out, you're grounded, or you can't play your Xbox or whatever it is, okay? The child that has, or the adolescent that has an easier adolescence, is a parent who says, why did you do what you did? And the adolescent says, I don't know. And so the parent sits down with them and reworks what happened with the child, the experience with them. And that's teaching the adolescent how to speed up to their faster brain and understand their behavior. So, but we'll get more to that when we get to adolescence. Right now, I want you to understand that we're born with a much slower brain, and it has to do with it. That's because the learning that occurs during this age group is immense, and we need a small, a less quick processing unit to make sure we learn that information well. Okay. And the other thing that we need to recognize is we're pretty much born with what's called a fully developed limbic system. The limbic system is also called the reptilian brain. It's been called the lower brain. Any species that has a brain has a limbic system, okay? What is mostly developing, starts to develop during infancy, is the cortex, which is this thing that sets over the limbic system, okay? And this is what gives us our higher thinking, our coordinated movement, our understanding of a space and where we are in space and time and a room, all of those types of things. And kind of an example of how underdeveloped this cortex is when we look at the visual cortex in infants, it's severely underdeveloped. In fact, when it up to, I believe, a few months into infancy, an infant only has eyesight up to about 12 to 24 inches. Beyond that, everything's fuzzy until this cortex starts to develop in the infant. And we also believe that that's why the female breasts are set where they are, because when the baby is feeding, you're at the perfect length that they could see your face clearly and make those emotional social connections with the mother. Okay, and that's why we believe that's why in humans, that's why the breast is located where they are. Okay, so what does this limbic system control? It controls things like memory, which is important, emotion, especially anger. It controls sensations that come into it. Our sensations are processed in the limbic system before it's sent to the cortical areas of the brain. It regulates through the brain stem and what's called the neolimbic system, this area in between the cerebral cortex and the limbic system, regulate autonomic functions such as breathing, heart rate, blood pressure. All of those things are regulated in this area, hunger and thirst. And as I said, these areas are pretty much developed when we're born. It's just this cortical area that tends to take time. The other thing that we should note about this cortical area is it develops from the back forward to the frontal cortex, okay? And this process, the frontal cortex actually doesn't become fully developed until late adolescence, like 18, 19, 20 years old, okay? And so it has a very long developmental period, okay? Now, what does the frontal cortex allow us to do as human beings? It helps us understand our social world. It helps with decision making. It helps with all our higher functioning areas that we think of that make human beings intelligent, right? And so this is why, again, when we're talking about development, asking a 2-year-old to explain why they slapped their brother and what they could do different next time doesn't work. And it frustrates parents because they think that the little infant should have the ability to solve their own problems and take care, because after all, as adults, we're able to do that. Why can't this little infant do it? And lots of parents get frustrated, and in a sense, it's an ignorance to know that these higher areas, this problem-solving areas of the brain, are what develop last. And if we want them to develop in a healthy way, again, just like my example with the adolescent with their myelinated brain, you have to walk the child through it. So that's what's going to develop this area, is helping that child understand things like anger, things like frustration, things like what can you do next time? Instead of asking the child what they could do next time, providing options and saying, let's do this or this or this. And this is also, there's been a lot of literature lately about physical punishment. And we're finding that physical punishment has a bearing on that frontal cortical area, such as spanking and slapping and hitting a child, to where we're finding that children who were spanked all the time and all those actually don't have well-developed decision-making areas within the frontal cortex. They tend to be more delayed. And so even just when a child does something bad, just slap them on the butt, that's not helping their development at all. It's just relieving a parent's frustration. So the other area of the brain that tends to be underdeveloped is the cerebellum right here. And sometimes people call this the miniature brain. But what the cerebellum does for a human being is it helps coordinate movement. So for example, making a sentence is a good example. So saying, I am Curtis, that sequencing was created in the cerebellum. Your ability to walk a straight line or write with a pen is all coordinated through activities in the cerebellum, okay? And that's one of the things that if you've ever noticed, like a boxer who boxed all their lives, they didn't have all the safety procedures that are placed in modern boxing and stuff like that. They tend to have trouble with speech coordination. They tend to need to use a walker or a cane to get around. And that's because the cerebellum, if I can draw this, sets just on the bottom of the skull right here. And then it goes the rest of the way around. And the inside of the skull, unlike a lot of the plastic ones and whatnot, the inside of the skull is actually not smooth. It's actually rough. It's almost like sandpaper. And what we have found with boxers like Foreman and all these other ones that tend to have speech problems and coordination problems is because of the pounding on the face. What has happened is, just like sandpaper, parts of the cerebellum get shaved off with constant hitting to the head. And so their parts of their cerebellum have basically been sanded off because of all the hits they've taken to the head. And that's why we see a lot of boxers who have coordination problems, okay? But this is underdeveloped too when we're born. And then as the child learns how to grasp, how to talk and everything, the connections within the cerebellum become stronger and stronger. And you start to see more coordinated abilities to move, to grab, to talk, and all of those kinds of things, to where by about the age of 6, the cerebellum is pretty much fully developed. And then you're just making stronger connections as you continue to develop through the elementary and adolescent years. Okay. So there's some other things to think about when we think about especially infancy and what happens through the early childhood years. Is the first thing is plasticity, and that's the ability for an immature brain to change in form and function. Okay. Um, so an example of this is there's some infants where one of their hemispheres, the right or left, was taken out in infancy because it was damaged. It had some type of neurological issues. So they do a hemispheric and dissect half of the hemisphere. Okay. And so if we look at the left hemisphere, it has a lot to do with speech and understanding sounds, those types of things. And what we found is if the less, for example, if the left hemisphere is removed, areas within the right hemisphere will take over that functioning and will utilize some of its space to deal with language and understanding sounds and all those kinds of things. So, but this has to happen early in infancy. And that's why a lot of time when an infant is born, if you do have a worth it doctor, the instant thing they start to do is check the child's nerve reactions. That's why they poke them in the little foot to see if they have, if the foot will react or have a reaction to it. They will do things, flash the lights in the eyes. They'll do some hearing things and stuff like that. And they have a whole list of nervous system tests that they do right when the infant is born. And if the infant then fails those, the sooner you get the infant into treatment, the more likely that the brain, if they have to take out areas of the brain or do something, other areas of the brain will take over that functioning. Now, this plasticity as we age gets less and less and less. And so when we're in middle adulthood, if we have to have parts of our brain removed, some of the brain, other parts might take over some of the functioning, but not all of it. So this plasticity kind of weakens as we get older. Within the baby's brain too, we have a lot of sypnogenesis. That's when our nerve cell makes new connections to other nerve cells. And we have this huge explosion in infancy to where our brain almost becomes oversynaptic in some ways, to kind of exaggerate this point. And this is why I mentioned in this course that between the age of 0 to 6, the average child will learn anywhere from 50 to 60,000 words, I believe it was. Okay, because they have that capacity because of the sypnogenesis. Okay, now again, as we age, our brain's ability to make new connections becomes weaker and weaker and weaker. That's why it's harder for an adult to learn a new language than it is for an infant or a child in early childhood. Okay. Now, what happens when we're not using certain areas of the brain is those connections start to prune off, and it's called the use it or lose it phenomenon. And probably the best example of this is talking about language. Okay, if an infant is not exposed to a wide array of sounds, at around the age of 2 or 3, they stop to be able to hear those sounds at all. Okay, This is why when you hear someone talk in a foreign language, you can't hear the breaks in the words. It sounds like they're just doing one extended sentence with no pauses in between words. In reality, believe it or not, that's how we actually sound. That's how, if you didn't know anything about the English language and you didn't hear English at all growing up, you wouldn't hear the breaks in the words I'm saying. You wouldn't have heard the break that I just said. So you would have heard it as you wouldn't be able to hear those breaks. Okay. And it's because of this pruning that happens. If you're not exposed to another language, if there's sounds unique to that language, you won't be able to hear it. Okay. My wife was a primary, her first language was Spanish. And then she developed English through school and through Sesame Street, as we say. And there are some times when she's speaking Spanish and I try to repeat it, I don't say the full words. And it's not because I'm not trying, it's because there's certain sounds in the Spanish language that I was never exposed to in early childhood that I simply don't hear. And therefore I can't reproduce it in word. Okay. So this is that example, though, this ability to hear sounds, the ability to hear breaks in words in your language, all of these things are part of this pruning process. If the child isn't exposed to it, they won't, those things that would have created the brain to hear those sounds pretty much just go away. They're pruned off. Okay. The brain also develops in two directions. One is called experience expectant, and then the other one is called experience dependent. Okay. Experience expectant is our brain is designed to achieve certain things, such as walking, talking, being able to feed yourself, be able to shelter yourself. And so the brain, based on the experience in their world, so, using a spoon or a fork or going from crawling to walking, depended upon the culture that child is raised in. Some cultures don't use spoons and forks, right? Your brain starts to develop in those directions without being dependent on the experience. It seeks those experiences out. That is versus experience dependent, okay? Meaning that the reason why a child is developing a specific thing is it's dependent upon the experience of the child. So for example, emotional reaction is an experience dependent reaction. Certain cultural things. So whether you say thank you or in some cultures, in Western culture, it's rude to belch in front of someone. In other cultures, it's considered respectful. And the brain learns this not because it's going that direction, but because it's experiencing it in that context, in that situation. Okay. And both of them combine to develop what's going to eventually be the personality, the way of being, the identities that this young infant is going to take on later in adulthood. So what I want to talk about for just a few more minutes is sensations and perceptions. Okay. So just to kind of connect these two, sensations is the process of getting information into the system. So for example, with the eyeball or the eye system is when certain waves of light hit the back of our eye to our nerve receptors for vision, that certain wave will make certain cells go off, which then that light energy then is converted into neural energy and goes to the occipital lobe, to then process to create our perception. Our perception is our interpretation of a sensation. And it's important to keep those things separate, because what we see in our world isn't necessarily what we are sensing, okay? And probably the best example of this, if you probably heard this if you took the Psych 101 class, is we all actually have blind spots. Because when the nerves exit the back of the eye, in the center of the eye, in that exit, there are no receptor cells. And so technically we all have blind spots through our pure vision sensation system. But when that energy is sent back to the occipital lobe uses memories and expectations to fill in those blind spots. Okay, that's a simple physical example. There's other examples as well. We can get into expectations from memories, learning, all those kinds of things that make our sensations and perceptions not one-to-one. Okay. There is an important thing that starts to develop through infancy. We've seen this start at as early as 4 months, but it becomes fully developed around 18 to 24 months. And that's our mirror neuron system, okay? And it's a very important process for especially things like social learning and emotional learning, okay? Is what basically the best way to explain mirror neuroning is that when you are really paying attention to someone else, the neurons in their brain start to fire in your brain, okay? I don't know if you've ever get kind of bored in a movie theater and maybe you're watching an action show and they're in a car chase, and you start seeing whenever the car makes a turn, everyone's head kind of goes that direction. And then when they make another turn, and then when there's something surprising, you see these startle reactions. Well, what we have found is when the stunt person performed those acts, those same nerves that was firing in the stunt man's head, later on, when people are watching the movie, start to fire in the audience head if they're really into the movie and they're paying attention to it, okay? This is what we call our mirror neuron system. And this becomes the importance of facilitating imitation in newborns. When you say an infant and a young child is a sponge, it's because literally their brain is lighting up when they pay attention to you the same way your brain is lit up. So, and this is an important system to teach communication, social interaction skills. It's the basis of the human emotion of empathy, and that's truly understanding the experience of others. It has implications for later on in the course, we'll talk about something called emotional intelligence, which is basically the ability to read the emotions of the room and give a proper and correct reaction. And it all starts at this early phase of infancy and helps the brain develop and understand emotions, communication style, and social interaction. So as I mentioned, we'll talk about the development of our 5 senses. As I mentioned, when we're born, we have very low visual acuity. We have 2400 vision, which if you know, the perfect human vision is 20/20. So this one has a ways to go from being visible, or as you would say. The other thing that we have learned is that infants are attracted to what's considered high contrast, especially in faces. So what do we mean by high contrast? So when we look at this picture, we have these colors, and then we have a low contrast, black and white, and then we have high contrast. So the hair is a little bit exaggerated. The teeth are, you can set aside the visual cues of the face. infants are more attracted to that high contrast than they are to colors and low contrast. And this is why it's recommended now, like in a child's play area, you don't use a lot of colors and a lot of playful things like that, that instead you just make sure there's a good contrast between spaces, okay? Because the colors and everything in a room actually are confusing the infant's brain. And so if you'll notice, if you could try this with an infant, if you go into an infant's room and it's all colorful and everything, take them to a different area of the house where there's a lot of contrast. And that actually has been shown to actually calm the infant down. So something to kind of think about if you are a mom or a dad raising an infant, okay? All right, so hearing, one of the things that we do know about infancy is that they do have a good acute hearing. In fact, we have found that prenatally we're exposed to mother's voice and heartbeat. And I want to make this clear because a lot of people say, well, I should play music to my infant and all that stuff. And while that was promoted early on in the psychological sciences, the science on that has been very, very shaky, because what the infant is hearing is mother's voice according to how mother hears it, okay, not how others hear it. And let me kind of explain this. If you've ever recorded your voice and you play it back, I'm willing to bet your voice sounds different than how you hear it, okay? That's because when we're talking, we're not hearing the sound waves that we're producing. They're going the opposite direction of our ears. What we hear when we're talking is the vibrations in our jaw going to our sensory areas of the ear and producing sound, okay? Same with the heartbeat. The reason the infant can hear the heartbeat is because of the vibrations it makes, okay? So when we say an infant hears, what they're hearing is the vibrations that are caused naturally by mom's vibration in her jaws to her ear and heart, the rhythm of the heart, okay? We know that newborns will have a preference for mother's voice within 3 days of birth. So they externalize the sound of mother's voice, and they'll have a preference because they've connected it with what they heard prenatally. Smell, they can react to mother's smell within 6 days of birth. Taste preference are usually for sweet over salty, sour over bitter. These are kind of averages. Some infants love salty and bitter, but for the majority, it's more of the sweet and whatnot that infants enjoy. And there is some evidence that infants can have taste preferences due to prenatal exposure to different foods. And so there is evidence heading in that direction as well. Pain and touch. So we know that infants are soothed by touch. And contrary to previous belief, infants can feel pain. Believe it or not, infants, the brain areas of the brain and the cortisol going on in the infant's body when they're being born, they are truly feeling the suffocating, crashing feelings of birth. Now, so is mom, so keep that in mind. But we're finding more and more evidence that this accounts for what's called infant amnesia. Because if you can think about how painful it is to be an infant, getting freshly exposed to light, to sounds, being squished through mom's pelvic bones, being handled in different ways, and you can't control how you're being handled and all those things, probably is really painful. And we can see the pain areas of infant brains going wild, okay? And it's probably a brain mechanism that creates infant amnesia so we can forget about all that physical pain and move on instead of being traumatized by it and what we went through as infants. So the other thing that we do start to learn in infancy, and it becomes stronger and stronger through the early child years, is this idea of cross-modal transfer. So, and what cross-modal transfer is perception of one sense and that enables recognition in another sense. So the example here is you can physically see your phone and hold it outside, but when you reach in your pocket and pick your phone out, or you reach in your purse and pick your phone out, you don't have to see it in order to see that it's your phone. You're using a different sense of feeling instead of seeing. Okay. We know that newborns have this, but only for some things. Okay. So, for example, the touch of mom's face versus the sight of mom's face. It is an example of newborn cross-modal perception abilities for things that they've touched and not seen. Okay. And we also have come to understand that this is why it's important to have toys in a infant and newborn's life that are both interesting visually, but also kinesthetically or touching. So you'll notice like this toy here has all kinds of textures on it, colors. You can make out what it is. I think it's a little bird. And so there's going to be that cross-modal perception and identification. And having these kind of different textured toys and all this helps this area of the brain that'll give rise to more cross-modal transfer of perceptions later on as the child develops. Okay. So let's talk about infant growth and motor development physically. As you've probably noticed with most infants, their head is very large compared to their body. Again, when this isn't seen in an infant, they'll do some extra tests because an underdeveloped head can be a sign of some developmental dysfunctioning that could be going on. And you'll also notice that most infants are usually born with a large eye, smaller nose and mouth, kind of fatty cheeks. And we don't know why, we think this is an adaptive trait, because if infants didn't have those cute features, because they are in constant need of caring, and it can be exhausting and it could be very labor intensive. Moms who don't sleep for a year understand this after giving birth to an infant, understand this idea. It's believed that these features make it so we don't get over frustrated with the infant and stop caring for it. That's kind of the evolutionary explanation of why infants are born with those quote unquote cute features. We know that babies' weights will double by 5 pounds and triple by 1 year, and add about 50% body length in just 1 year. So this first year is a rapid growth period. And it goes back to our idea of this is probably why we have infantile amnesia. If you think about bones and everything growing that quickly, it can be very painful. And so those are some things that we have to note. We notice that in infants, there's longer sleep periods, more naps. And this is important to understand, is it's when we're sleeping that all that synaptic genesis is going on. That's when the brain is building all of those connections. And if you think about everything an infant learns in that first couple of years, it demands a lot of rest and a lot of sleep. And the more sleep you see and naps you see in an infant, while an infant going well into early childhood, that's usually associated with a growth spurt that is about to happen. So we are born with certain reflexes that kind of help us develop and grow. Okay, so a reflex is a pattern involuntary motor response, and again is controlled by that limbic system. So they're there and are meant to help us survive. And they begin to disappear. These reflexes that we have when we're born tend to disappear as that cortical area, that cap over the limbic system, starts to develop more and more and more. And again, the reflexes are one of the primary things that doctors check when an infant is born, because usually the absence of a reflex can indicate neurological problems in an infant. So what are some of these reflexes? Well, we know, for example, the sucking reflex in order to get milk starts to disappear around the 2-month mark, to where the infant has to take over that reflex. And you'll notice around 2 months, infants start to kind of struggle with feeding, because this process of the sucking reflex being a reflex, an automatic process, starts to diminish, and it demands the infant then to kind of learn how to suckle and suck for milk. Okay. The crawling reflex, when a baby places, this is not the crawling on hands and legs. This is when a baby is placed on their tummy, they'll move their legs and kind of make a crawling motion. This reflex prepares the infant for later on to use its legs, but it also starts to disappear around 2 months. The more or the startle reflex, this is when a baby loses support or feels like she is falling, or hears a loud sound and does basically a startle reaction. This too stops around 3 months. And these will all be posted on Canvas, and you kind of can go through each of these and kind of see when they disappear. There are 2 reflexes that we're born with that stay. They never disappear. One is the gag reflex, and that's when we want to expel an object that is too large or has a wrong smell or something like that. And the blinking reflex. We blink every minute or so. We'll get into that a little bit later, or when we're exposed to bright lights. So these 2 reflexes never actually leave. They're the only 2 reflexes that continue into adulthood. Okay. All right, moving right along. And I know this is probably a little bit overwhelming with information. So again, I'll post these and you can kind of go through them again. Is motor development. So our ability to use muscles and coordinated movement. We start with gross motor skills. These are the moving of the large muscle groups. So being able to sit up, being able to crawl, then being able to walk, are all part of this larger muscle group. Then as we age, our fine motor skills, the ability to write, use our hands and fingers, our lips and our tongue, start to develop shortly after. Okay. And the same goes with myelination of our, again, I mentioned that in our peripheral nervous system, to our muscles and stuff, which are called motor neurons. they're largely unmyelinated, but quickly myelinate through as we start to use our larger muscles, and they myelinate from the head to so from the brain area to the other parts of the body. This is why an infant, one of their first feats is being able to hold their head. Not only does that have to do with muscle development, it has to do with the myelination that has to occur in those motor neurons in order for the infant to be able to hold their head. And then from there, they'll be able to sit up. Then from there, they'll be able to be more motor, okay? And we also myelinate from what's called proximodal. That's from the torso outward, so from the center of the body outward. So first comes our ability to hold our head. The second comes to being able to hold ourselves upright. Second is control over our arms and control over our legs. It starts from top, center, out. So this is just kind of that example of we start in our torso, arms, hands, then fingers. And that's kind of what proximal development looks like, at least with the arms and hands, okay? So again, this is some of the milestones we see with development, okay? And again, these are milestones. Not all children develop the same. And so we have the average, but then we kind of have this range of possibilities. So holding the head erect and steady, usually on average is about 1 to 6 months, but it can take up from 2/3 of a month to up to 4 months to fully develop in some infants. Sit with support, and we can see these figures as we go down. So we sit, we lift our head and shoulders, sit momentarily without support, reach with one hand, and you can see how these kind of develop again from that center head down approach to where by about 11.7 months, anywhere from 9 to 16 months, we're walking independently, okay? And again, this is just an important point to make. There's a lot of variability in these milestones, and so a child who isn't able to walk at 11 months doesn't necessarily have a walking deficiency, and we can even see some cultural aspects of this. We see, for example, studies done with Kenyan parents who bind their infants at a very early age, and so they're not able to move. Their ability to walk actually begins around 24 months because their bodies have been bound most of the time during those developmental periods. We also know that sleep has to deal with it, deals with when certain things develop. So if a infant doesn't get sufficient sleep, motor development can be delayed. And we also know that cognitive development usually outpaces motor development. So our thinking ability, and this is why, again, having a stimulating environment is important, but not an overstimulating one, like with multiple colors everywhere, okay? Is that cognition we see precedes the motor development we see, okay? And we'll look at cognitive development in our next section on Thursday, okay? But the reason I did bring up the Kenya study and the sleep study is these are all culture plays a role, remember, in development all around. And even when we get to puberty, we'll see culture, family systems really are the main determinant of when a child will go through puberty. And so we'll look at that when we get to that point as well. And this experiment, I think, is a good example of how cognition develops before motor skills. Okay, so we've asked the question, do infants have depth perception, which requires cognitive evaluation of a situation? And the answer to this is yes, as early as 6 months. You remember, when we look at motor development, infants are really starting to crawl and move around 6 months, right? But we see that depth perception, which is a cognitive process, develops just before that. Okay, and we can see this through the visual cliff experiment. So this is an example of this. Now, there's actually a glass plate, a thick glass plate right here. But if you're an infant, you're going this and you're looking down. Okay, around 6 months, most infants will stop at this ledge and look for cues of what to do. Okay, and so we have found, for example, parents who say no, 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 stop, don't go. Most of the time, the infant will not go across. Okay. However, even though they are seeing depth perception, if the parent is saying, come here, come here, come here, like this dad is right here, the infant will actually venture over this glass, and despite their depth perception. So we see in this visual cliff, the development first before the motor skill is, one, understanding that something has changed. That's the first thing. And then the second thing is they're using social skills, social cues to determine what they should do next. And thinking about that, that's what we mean by development of cognitive skills before motor skills. And I mentioned the sleep thing earlier. And you can see between newborn to 1 year of age, okay, we see that an infant, I believe this is about 18 hours, I think. And then it's the need steadily goes down as the infant goes through that first year. And so this again has to do with that, how much neurogenics is going on during this period, okay? So as it says, here's the words for it. So newborn, the sleep is around 16 to 18 hours per day, 6 months old, 12 hours or more with daytime naps. And there is this, I do want to bring up at this point, I hear a lot of parents say they want to train their child to be asleep at certain times and whatnot. And so a very common method that has been promoted by some idiots in medicine is the cry it out method. Sorry, I didn't mean to use that derogatory term, but it kind of is. So it's where you leave an infant to cry it out so it learns to go to sleep at certain times according to the parent's demands. I will tell you, this was promoted in the 50s and 60s, and it has had dire consequences for individuals. This is some of the basis for things like not being able to sleep while you're an adult, not having a good sleep-wake cycle through early childhood into adolescence and stuff like this. And there's been a lot of studies that have shown that the cry it out method is more traumatizing than helpful. That really infants come with a natural reflex of when they need to sleep and when they don't. And when you force sleep and you force wake, you're missing out on the infant's brain actually making the connections that it needs to make during that sleep period when the infant is needing sleep or not needing it. And it also, research has shown that infants will fall into a natural pattern without it being forced on them. So just wanted to bring that up at this point. Okay. And then I just wanted to bring up before we close up tonight, I know we just have a few minutes left, and I know I just provided you with overwhelming amount of information, is just stress and coping, okay? So the hormone associated with stress is cortisol, and it's a hormone that prepares the body for a threat or a challenge. It basically is the body's chemical preparing the body for fight or flight. And we know that in small amounts in infancy, it's actually a good thing. So to say that an infant should not be stressed or in some way is kind of a bad advice. Now, stressed versus physically hurt or punished are two different things. But an infant experiencing small amounts of stress is actually promotes their development. However, when the infant experiences chronic stress and constant stress, this can become very overwhelming to the brain. And in fact, in a lot of situations where an infant has come from, has been born into a family full of family violence and constant chaos and stuff like that, we actually have seen damages in certain brain areas of the infant. So it can actually, when it's chronic and overwhelming, it can actually damage the brain system and the brain itself. However, the good news is the good news is that the implementation of actually a sensitive caregiver can actually reverse this stress effect in infants. So let's say an infant is constantly stressed in the first 6 months of life, but then an intervention of some type comes into play. Maybe the grandparents get involved or something happens where at that 6-month mark, maybe they have a caring and sensitive caregiver. Any damage that has been done at that point can actually be reversed. And so that's a good thing to just note, okay? All right, I am going to stop sharing. I know we don't have much time.